So this is a lecture, part of lecture 5.1. So this is going to focus on thermodynamic equilibrium for vapor-liquid equilibrium. So essentially here what we're doing is we're going to derive expressions using the fugacity equations that will give us the modified Raoult's law as well as the Raoult's law, and also just a general expression for the correlations between the vapor phase and the liquid phase. So all of the foundation of what we've done so far is basically what we need for this lecture from the previous lectures. So what did we kind of conclude from the previous lectures? We said that the fugacity in the vapor phase is equal to the fugacity in the liquid phase, which is equal to the fugacity for the saturated fluid. And this is the case at constant temperature and pressure. And these are for, any component I in this case. And then we also looked at mixtures. So for mixtures, instead of this fugacity F that we wrote fugacity with a hat. So this is for vapor and this is for liquid. And from last class, we said that for the mixtures at a given temperature and pressure, that these two are also equal. So again, at equilibrium conditions for all components, right? Whether you have two components, three, up to n components. Other equations that we looked at was the fugacity coefficient for mixtures. So this is what we see here. We added a hat for the coefficient. This is our fugacity in the mixture divided by YIP. So this would be the case of the real divided by the ideal. And for vapor specifically, we can write this as, so we can rearrange this, multiply this both sides by YIP to solve for the fugacity. So the fugacity for the vapor in a mixture is equal to the coefficient of fugacity multiplied by the mole fraction in the gas phase times the total pressure. So our goal now is to find an expression that will, have the liquid fugacity. And then what we're going to do is equate the two, and this is half of the equation. So you can kind of see in a way, if this part of the equation is equal to 1, then we already have part of the Raoult's law equation. So that this is YIP, which is the partial pressure of component I. So now we're going to move on and try to derive this expression, which is for the fugacity in the liquid phase. So we're going to start off with Gibbs energy analysis for mixtures. And here we're going to see Gibbs energy, the excess Gibbs energy for the mixture. So this is the partial again, the partial Gibbs energy. And this is for the mixture, which is kind of the real actual Gibbs energy, the partial Gibbs energy. And then here we have the ideal solution. So we saw from last class the ideal solution model and how the excess property correlates to this with the actual property of the system. So let's take this actual partial Gibbs free energy in this mixture for component I, and we can write this expression. So this expression you should be already familiar with what we've covered before, where this gamma is basically the integral constant plus RT times the natural log of the fugacity of component I in the mixture. This part of the equation, this is for the ideal solution. So what we have is, again, the partial Gibbs free energy equals to gamma T. Again, this is a constant, which is a function of a component I and temperature, plus RT times the natural log Xi Fi. In this case, this Xi Fi is actually the same as the fugacity, right, which is written like this. So the fugacity of the ideal solution for component I. So now what we're going to do is subtract these two equations from each other to get what? To get the excess equation, right? So we're going to get, so we kind of saw this in the previous lecture, but we're just going to kind of do it here in detail so that you guys kind of see this. So we're going to get, so we're going to subtract the two. So what we're going to get is the following. So we have GI E is going to equal to, so the gammas cancel out, so we're only left with RT, and then we have natural log of the fugacity in the mixture, so this is the real fugacity in the mixture for component I, divided by Xi and the fugacity of the pure substance. And what we said also in the previous lecture, that this is actually our activity coefficient. So this is gamma I, which is the activity coefficient. So we can simply write that in. So we can just say this is equal to RT natural log activity coefficient or component I. And from the summability relations that we've had given before, what we can find is if we add all of the partial properties, right, we get the actual property. So that kind of the system's property. So this is what the summability relations actually do. So let's just write that down. So summability relation. So we have GI E over RT is equal to the sum of the mole fractions. So in this case, we're looking at a solution. So we're going to use the mole fractions in the liquid phase multiplied by the partial properties. So again, here we're looking at excess because that's what we have, up here in the expression. So divide by RT, and then this is going to equal to the summation of Xi multiplied by natural log of gamma I. Why? Because we essentially just move this to the other side, so we divide both sides, so we're only left with gamma I in this case. So we're going to use this expression actually in the coming lectures, so we're just going to, keep this in mind for later. So will be used in the lectures to come. So this is kind of like a side note, but now we're just going to go and focus more on the fugacity or the activity coefficient that we just came up with. So for the vapor-liquid equilibrium from acting coefficients or the activity coefficient for liquid phase, let's write this down. So we have vapor-liquid equilibrium from activity coefficient, liquid phase. So we have gamma I, liquid phase. Let me write that again. Liquids equal to fugacity in the liquid divided by, for the mixture, divided by Xi, fugacity of the pure liquid. So this is all from kind of what we see up here. So now, in fact, we can rearrange this, right, to solve for what? For what we need. This is what we need. We need this an expression for this fugacity in the liquid phase. So we're going to rearrange this expression to get the following. So we have the fugacity in the liquid phase in the mixture is equal to Xi gamma I, which is the activity coefficient of the liquid, fugacity in the liquid phase. So that's the pure substance. And already since we said before, right, since the fugacity in the mixture at equilibrium between the vapor is equal to the fugacity in the liquid phase. So, and from equation 1, so up here we called this expression here equation 1. So that's for the fugacity in the mixture of the vapor phase. So we have the fugacity coefficient, the mole fraction in the gas phase, and the pressure. So we're going to equate those. We're going to plug that into this expression, and then we're going to plug this into this expression. What are we going to get? We're going to get, and equation 1, we're going to get yi, and then the fugacity coefficient, V, times the total pressure, P, is equal to mole fraction in the liquid phase times the activity coefficient in the liquid phase times the fugacity of the pure liquid. So this applies for, I equals, 1, 2, and so on. So I equals 1, 2, and so on. So we've already seen an expression to solve for what? For the fugacity of the pure substance, liquid, using the equations we've derived before. So let's write those down. So for liquid phase fugacity, assuming that the volume of the liquid is equal to, say, the saturation volume and it's constant, or an average volume is constant, we said that the fugacity is equal to fugacity coefficient at saturated conditions times the saturation pressure times an exponential, which has the average volume, times the pressure minus the saturation pressure, pi sat, divided by RT, as we see here. So this is the general expression, and this expression would basically be plugged into where? To the expression that we have above right here. So that is what the liquid phase fugacity. But if we combine these expressions, so if we combine the one above and this one, it becomes a bit complicated. So there's a generalized kind of form that we're going to write where we have a simplification. So combining the last two equations, what we're going to write is yi, then we have this kind of new variable that combines some of the coefficients of fugacity multiplied by total pressure equals to mole fraction in the liquid phase times the activity coefficient times the saturation pressure. So this is what we're going to call equation 2. All right, so this new variable here that I just kind of mentioned is basically our fugacity coefficient in the vapor phase, is what we see here, divided by this and all of this. All right, so let's write that down. So this is what we're going to see here. Another thing that you would have probably already noticed is when I wrote this expression, we just see the pi sat here. So this is from there. So that's the only thing from that expression that remained in here. And the rest of it is hidden in this variable that we see here. So let's write down the expression for this. So this is actually equal to, as I mentioned, the fugacity in the vapor phase. So this one here, divided by this, multiplied by what we see here, but the inverse of it. So we're going to have, again, the fugacity in the vapor phase for this mixture, component I, divided by fugacity coefficient at the saturated conditions, component I, times the exponential, and here we're going to have a negative because we moved it from one side to the other, the volume of the liquid, and then pressure minus pi sat divided by RT, as we see here. So the one thing to know about this factor here, we've already kind of seen this factor before, and we already, I believe we called it the pointing factor. So this factor for low to moderate pressures, so when this pressure, is similar to the saturation pressure and so on, this in fact, goes to 1. So this pointing factor for low to moderate pressures is going to be approximated as 1. So then what we end up with is essentially, this new variable is going to equal to the fugacity coefficient in the vapor in this mixture divided by fugacity coefficient for the saturated conditions for this liquid. So in this case, this in a way is a ratio between the two. And, for simplified expressions, what we're going to see is that we're going to simplify this variable to equal 1. And that's how we get the Raoult's law. So let's write those down. So how did we get Raoult's law in this case? So if this fugacity coefficient ratio is equal to 1, and if the activity coefficient is equal to 1 in equation 2, which is what we see up here. So if this is 1 and this is 1, what do we get? We get Raoult's law, right? Yi times P, Xi times Pi sat. So we get Raoult's law, which is Yi times P equals Xi times Pi sat. And you guys already know this. So this is mainly used for ideal solutions. So mainly used for ideal solutions. And obviously the temperatures for each component is below the critical temperature. So temperature for each component is below critical temperature, TC. So then the last thing here, just to show you guys for the modified Raoult's law, simply, if this new ratio of the fugacity coefficients is equal to 1 and gamma I does not equal to 1, so that remains in the equation, in equation 2, right? Then we get the following expression. So we get modified Raoult's law, which is Yi P equals Xi, activity coefficient Pi sat. And this applies for low to moderate pressures. And, it's works well in a variety of systems. So great for a variety of systems. All right. So this is all I want to do, just to kind of derive these expressions for the Raoult's and the modified Raoult's law, and also to show you, this excess equation where we have from the summability relations, the excess gives energy over RT is equal to the summation of Xi times the natural log of the activity coefficient. So we're going to be using that as well later on for kind of these vapor-liquid equilibrium systems models. All right, so that's it. So we'll continue with the lecture. So this is just an extra for the derivations. So you guys, if you have questions about how did we come up with these expressions, you can derive it. All right, thank you.